Hello, today we are going to learn a different way to find volume of solids that are revolved. We have the shell method today. So you can kind of think of the shell method as the little nesting dolls, how you're just putting little shells together. Let's take a look at a little animation to kind of get us in the idea of what's going to be going on with this shell method. So we start out with our basic curve and we draw little sample rectangles. This time though, we draw our sample rectangles parallel to the axis we're revolving around. Okay, and so you can see as I rotate that sample rectangle around, I have created a shell. Okay, and so when we find the volume of the shell, it will be a little different than finding a washer. We'll talk about that in a second. So now I have infinitely many shells that are going to be put together. So again, you're thinking of the little nesting dolls as they rotate around, and you can kind of see the solid that is getting formed by putting all these shells together. Okay, and then they'll make it a little less rigidy here, and you can see this is the solid that's formed by rotating that curve around the y-axis. Okay, so let's go back to what we did before. Just remind ourselves how we did a problem like this. So I have this line, and I'm going to take the area underneath it and rotate it around the y-axis. So some of you might say, hey, this is just a cone, and I can just go ahead and say, well, I know the volume of a cone is 1/3 pi r squared, and I can see times h, and I can see the height of that cone will be 2, and the radius of that cone will be 1. So yay, no calculus required. But where would the fun be in that, right? 2/3 pi. Okay, so we want to come up with, or we want to verify that the washer method works and the shell method works, because we are all very comfortable with our geometry formulas and the fact that, okay, that works. So that must be our answers, 2 pi over 3. So can we get it the same doing what we've done before? So again, kind of like what you've done with your Hershey's Kiss project, we are splitting up our area into little rectangles, infinitely many, and you can see that the width of that rectangle is delta y, which means we are going to be integrating with respect to y. Okay, which means the whole integrand needs to be in terms of y. So instead of y equals 2 minus 2x, I have to solve that equation for x, and I will get my radius to be y minus 2 over negative 2. So as you can see, we're going to use a dis method because there's no hole. And we remember the formula for our dis method is just pi r squared. And remember our r is our function here, which is y minus 2 over negative 2 squared. And we are going to be integrating because our y values start here at 0 and go up to here, which are 2. We're going to integrate that, and if we punch that through our calculator, we will get 2 pi over 3. All right, so just in case you didn't believe me, I shoved it through my calculator. I got 0.6 repeating, which we all know is 2/3. Place a pi after it, and we end up with 2 pi over 3. Okay, so now we are going to do the shell method. So notice the difference here. The rectangle in the washer and dis method, in this case the dis method because there's no hole, is perpendicular to the axis it's going around. Whereas the shell method, the rectangle is now parallel to the axis it's going around. So if we think about this, we are going to end up having this shell over here. And if you think about just taking it and cutting it in, slicing it down the center here, and then laying it flat, it will look like a rectangular prism, kind of like this guy over here. Okay, and so we need to find the volume of one of these guys, and then we add them all up. Okay, so again, if you look at how the shell is created, This here is the width of the prism, which is going to be a delta x. So therefore, this is delta x. Okay. The height of the rectangle is going to be the function. Okay. And since it's delta x, we know that we're going to be integrating with respect to x. So this function is just 2 minus 2x. So therefore, the height of the prism over here is just 2 minus 2x. Okay. And then our width of our rectangular prism, or our shell that's flattened out, if you look at where that width comes from, it comes from laying this guy flat, which is just the circumference. So this is just the circumference, and the circumference of a circle is 2 pi r. And so now we got to figure out what r is, but r is the distance from the rotation, your axis you're rotating to your rectangle there. So you can see that is your r value, which is just x. Okay, so therefore our circumference is just going to be, all right, 2 pi x. All right, so the volume of this guy is 2 pi x times 2 minus 2x times delta x. And so if we add up infinitely many of those, we know our delta x goes to dx. And we can put our 2 pi out front of our integral. Then we have our radius, and then our height of our rectangle. And we integrate it from 0, because now we're doing x's, so 0 to this point over here, which is 1. Now, if I was going to go ahead and integrate this by hand, I would first do the multiplication, always algebra first. All right. This is a pretty easy one to integrate by hand, so let me just do that. I probably can do that quicker than actually going to my calculator. I should have parentheses around that. So that's x squared minus 2/3 x cubed evaluated from 0 to 1. And so I have 2 pi times 1 squared minus 2/3 times 1 cubed, and then minus 0, right? Minus 0. And so I have 1 minus 2/3, and we all know 1 is 3/3. So 3/3 minus 2/3 is 1/3, and we have 2 pi over 3. All right, so we got it using our geometry formula, we got it using our Washer formula, and we got it using a shell. So some of you are thinking, okay, why would we ever use shell? I've got other ways to do this. Well, sometimes we have to use shell. If you think about this guy right here, this curve, and you drew in a sample rectangle trying to use the washer disk method, you would struggle to find this length right here, right? Because it's the function minus the function, and now we're at 0. It's just kind of craziness, doesn't make sense, right? So you could say, well, I can solve that by go ahead and put a line there, and I'll just integrate it twice, which is possible, but unfortunately, this equation is y equals x minus x cubed. And if I'm going to draw my rectangles horizontally, that means I'm going to be integrating with respect to y, which means I've got to solve this equation for x, which I can't do. So we are now forced to use our shell method. So I'm going to draw in my rectangles. So they are parallel to the axis I go around. And I know the shell method, I'm just going to have the 2 pi that represents my circumference. Okay. I can see here that that's a delta x, so I know I'm going to be integrating with respect to x. I can see my x is going from here, which is 0, and then to this point, which I can get by just setting this equation, 0 equals x minus x cubed, factor out an x, so that's 1 minus x squared, which is x times 1 minus x times 1 plus x, if that's the difference of squares. So you can see our three zeros are 0, 1, and negative 1, but we're only looking at the first quadrant, so we don't have to worry about the negative 1. So we know that this goes from 0 to 1. The radius, so again, think of this as being a shell, right? It's going to go around over here. So your radius is from here to here, which is an x, just the length of x. So our radius is x, and then our height of our prism is going to be our function, which is just x minus x cubed. Okay, then we can put that through our calculator, or we can integrate it by hand. Either way, I do this, I'll end up getting 4 pi over 15. So do expect to be able to do it both ways. We do expect you can still do it by hand. All right, so then we're done. 4 pi over 15. Now, there is another reason why the shell method is kind of nice. So if you look back at the equation y equals x squared plus 1, x equals 0, x equals 1, and y equals 0, we've got this region. And we've done this before. We did this in the washer method, and you may recall that we had to set this up into two different integrals, right? Because you had to break it up and see, okay, I've got that, you know, solid bit there, which is going to be a disk method, and then I've got this bit here, the top half, which you're going to have around here, which you're going to have a hole, so you're going to have to do the washer method here and set up two different integrals, whereas if you look at the shell method, you can see that I can create horizontal, or sorry, vertical rectangles that will now just go ahead and solve the problem of not having two integrals, because all of these rectangles will be covered under the one function. So sometimes we use the shell because we have to, and believe it or not, sometimes we use the shell because we really want to. It makes the problem easier. Okay, so you can do this one if you want both ways. I'm going to skip to a different problem that's a little more unique. We can answer that question if you need it later. All right, so here's my new one. I have y equals x and y equals x squared, and I'm going to go around the y-axis. Okay, so I got this region here bounded. I'm going to go around the y-axis. So again, I need to make sure my shells are parallel to the axis I'm going around, which means I'm going to be integrating here with respect to x. That's kind of where I start. Okay, then I might just see where my x's go between, because I know this has to be x's here. So I say, where does x equal x squared? And so where does x squared minus x equals 0? And we do the same sort of factoring we did before. And we can see that's going to happen at 0 and at x equals 1. So from 0 to 1. Okay, now because of the shell method is circumference, the 2 pi is just always out front. And then our radius for the shell, again, think of your shell as being over here, right? Kind of, I know that's kind of ugly, sorry. And then your radius then would be from here to here, okay, which again is just an x. So our radius is just x, and then our height is the length right there, which is just the top function minus the bottom. Okay, and our top function you can tell is the line, and the bottom function is the quadratic. Okay, again, you can go ahead, integrate this by hand. And if you were going to do that, x squared minus x cubed, and then do your power rule, 2 pi. I should have parentheses around that. x cubed over 3 or 1/3 x cubed minus 1/4 x to the 4th, evaluated from 0 to 1. Plug it in. It's always nice when it's 0 and 1 because it makes the calculations really easy. So I have 1/3 minus 1/4. You put 0 in there, it's gone. So now I have what? If I add my fractions, I have 4/12 minus 3/12 times 2 pi. So that ends up being 1/12 times 2 pi, or pi over 6. All right, let's try one more and just kind of mess with that radius not always being x. A lot of times it's just x. If you're just going around the y-axis, it's just going to be x. But we have this scenario where we're going to go around the line x equals 2. Okay, so now you got to think of your, again, you want to be parallel to the axis you're going around. You want your rectangles to be parallel. So you think of your shell over here, right? And so your radius, I'll kind of draw it in here a little bit. It's not going to be beautiful. Sorry. All right, so it has a little bit of... All right, anyways, so here's my radius now is from here to here. That's my radius. Okay, and if you think about that length is this length, which is 2 units long, minus this piece, right? Whatever your function leaves you. So, and that piece is x. All right, so if you take away x, you end up with your radius. So from here to here is just going to be 2 minus x, because this piece right here is x. Okay, so looking at that then, let's write our integral. So I know the 2 pi goes out front. Our radius now is 2 minus x, and our height of our shell is just this length right here, which is your top function, which is your cubic function, minus your bottom function, which is just your line y equals 1. And we're integrating with respect to x. Our x goes from here, which is 0, to here, which is 1. You don't count x going to 2 here because you just want this region, this whole region. And in that region, x only goes from 0 to 1. So I go from 0 to 1, and then I plug it into my calculator or integrate it by hand. Right now I end up with 2 pi times 29 30ths, which ends up being 29 pi over 15. All right, hopefully that helps you see another way to find the volume, and you will be able to do it both ways, washer and shell now, and find, when you need to use one or the other. All right, see you in class.